Hello. I posted a video about using the MPU6050, and it's a little bit of the practical side to it, but the theory is a little bit not too good because I didn't have much detail. So I thought I'd put a lot more detail in this and show you exactly what I'm doing about using the Kalman filter to get better results in the MPU6050. If we move on to the next slide, well, it doesn't seem to be. Oh, there we go. So there's the MPU 6050. It's a 3-axis gyroscope and 3-axis accelerometer. That's just straight from the online information. It's got a digital motion processor. So we say it's got 6-axis motion fusion. That means it's accelerometer and gyro built into the one chip. And a lot of these devices are actually available in mobile phones already embedded into them. Whether they've got Kalman filters or not, I have no idea. I'm going to use the ESP32 microcontroller, which is a couple of years old. It's not very old. It's excellent microcontroller, and I did that on the other video. So straight to the actual. Oh, wait a minute. It's not changed. Ah, there it goes. So straight to the actual information, which is the continuous time state estimator. So we can represent the dynamic system, if you haven't looked at this in the theory, as x dot equals ax plus b unit plus d zeta, as x is a vector, a, b, and d are matrices, and zeta here is a vector of noise terms. Often we can omit b if we're just doing signal processing, which we are actually today. Just have x dot equals ax plus d zeta, where that's noise. We call this a stochastic system. It's a system driven by white noise, and it's a little bit sort of abstract at the moment, this, but we can take any transfer function and convert it into this, usually without this part here, it's not zeta, it's psi, the Greek letter here. Normally x dot equals ax plus bu, y equals cx, but we've got the additive noise at the input, which is called the process noise here, and additive noise at the output called the measurement noise. And these are both vectors. And here y is the output of the system, the clean output, if you like, driven by noise. And s is when you've got additive noise on top of that. And it's always white noise. And these two noise terms are uncorrelated v and psi rather. And we need a covariance matrix to describe the noise terms. They're usually diagonal to make them easy, Q and R, and I'll come back to that later. Now to get the best estimate of the state, that's what a Kalman filter is. We define an error, which is also a vector, x minus x hat. A hat here means a best estimate, or the linear least squares estimate, really. It means a time t, this is continuous time, given information up to time t. And the solution to this was found in the 1960s by Kalman and Bussy. It's called the Kalman-Bussy filter. I think this one is, anyway, it's the analog version, the continuous time one. The discrete time one, which we're going to use in a minute, was due to Kalman. It was done after he did the discrete version first, I beg your pardon. This one was done afterwards. The analog version was done after the discrete version, which seems a bit strange, but that's how it was. It's almost as if he was ahead of his time, really. This is the equation of the Kalman filter. There's, of course, a derivation, long, lengthy derivation for this. But the hat means an estimate, so it's x dot hat is ax hat plus bu plus k s minus c x hat, and that's the estimate of y, which is cx. That's just this bit in here, where you've got to find k, which can be a vector, it can be a matrix. It all depends. whether you've got multiple outputs or just a single output and single input and so on. Could be a vector, could be a matrix. K is found from PC transpose r to the minus 1 r is the noise covariance, where P is found from a matrix Riccati equation. This is a differential, a continuous time one. So what this gives you is a set of differential equations which are normally nonlinear, and you have to solve that, and it's pretty nasty. But although there are ways to do that, you can solve that, and it can be done in MATLAB as well. But in the early days, of course, it was a matter of how do you actually solve that equation, which is a matrix equation. This thing called P it's got to be positive definite matrix, which is called the error covariance matrix. It's defined as expected value of E times E transpose. I have another talk on Kalman filters, which perhaps explains this a little bit better, also online. This is the block diagram of the Kalman filter. This measurements goes in here. That can be a vector, as I said. That can be a matrix K. A is always a matrix unless it's a scalar system. C can be a vector or a matrix, again, depending on what it is. Now B here, it doesn't always exist, again, depending on whether it's got a control system that's got a set point that's not 0 or something, then that comes into account. But with a lot of filtering problems, this bit disappears. You don't have a B term at all. You've just got some sort of signal coming in here and a state estimate coming out there. So this is like a model of the system almost, but with this additive K term matrix and there's feedback around it. Notice that the Kalman filter itself has got negative feedback around it. It's always stable, it's guaranteed. Again, there's proofs going way back that the closed loop Kalman filter is always stable. You can, instead of solving P dot equals, that's going back to here, if the rate of change is 0, P dot is 0, then you can solve what's called the algebraic Riccati equation, which I think is a little bit easier, but even for small problems, that can give you quite nasty nonlinear algebraic equations to solve. And you can solve that for P if you can solve it, if it's solvable, and then you can get K from that. But usually we find numerical solutions because it's really too hard to work out analytically, apart from very simple problems. So this would, for example, if A was a 2 by 2 matrix, inevitably P is 2 by 2, so you end up with 4 algebraic equations. Because it's symmetric, often 2 of those are the same, so you might end up with 3 and 3 unknowns to find P. And as I say, it can be difficult, or some of them are solvable. So when you go to discrete time or sampled signals, which is what we're interested in, the Kalman filter, I'm going to come to the Kalman filter. This is the system description, changes from what we had here, which was x dot equals ax was bu. I'm missing out the b term because we don't really need that. So x dot equals ax was d psi. And I've called it, so in discrete time we use different letters for the matrices to avoid confusion. Otherwise, I mean, in some scientific papers they actually do, in the literature they use the same letters, like they can have ax plus d times that, but that actually should be a vector, I've just noticed. But here I'm going to use different terms because I don't want to confuse the continuous and the discrete. So x is the state here, xk plus 1. So this is a difference equation in the vector difference equation. And this guy here, which is noise, it's discrete noise, it can be a vector as well. And the additive, these should be bold as well. That's additive noise. S is the observation. So you're actually measuring S. And what you want to do is get an estimate of the state x, which we call x hat. And as before, in the continuous time case, we defined this error, xt minus x hat t given t. Here it's x hat k minus x hat k given information up to k minus 1. That means the estimated time k, sample instant k, given information up to and including time k minus 1. That means really what we've got is a one-step predictor. It's not really a filter, but usually we call it a filter. You can also get instantaneous filtering and what's called smoothing as well, and also prediction. There's some variations on this. We're not so interested in that at the moment. And we can convert from continuous to discrete time. Have been known for a very long time. One way is to do this power series method. There's a whole host of different ways to do it. This one I'm going to use because we can actually work this one out manually for our particular problem. And that's to say that you can expand e to the a t, which that's the relationship that you get between continuous and discrete. A is the continuous A matrix, F is discrete time equivalent, and they're related via exponential matrix. TS is the sampling interval in seconds. And you can expand that with a Taylor series, I plus AT, or a Maclaurin series, rather, 1 over 2 factorial A squared and so on. Now, normally you'd that kind of converges, so you might take 10 or 12 terms or something to win these higher order terms, provided A is stable, that converges down, and you get F from that. But the example that I'm going to look at is easier, and I don't need to take that many terms. I can just take a couple of terms and I get very accurate results just for this particular case, not for all cases. Anyway, this is a little trick. We can write this as I plus AT psi, and where psi is equal to I plus 1 over 2 factorial and so on. And we end up with this formula here. So to find F, we just work out I plus ATS psi and find psi from this power series. And then we can find G, which is our equivalent. So this is the continuous time, x dot equals AX plus BU. This is the discrete equivalent, xk plus 1 is fx plus GU. We can find a discrete equivalent, G is TS psi B. And that means we can convert from continuous time to discrete time. And MATLAB will do this for you as well, so you don't even have to do that. But that's how it's done. At least that's one way is how it's done. So our discrete time Kalman filter, just to say, was worked out first by Kalman, obviously, before the continuous time version. Is kind of similar, but not quite the same. Instead of a Riccati equation, which is a differential Riccati equation, it's a difference Riccati equation. You've got, this is the error covariance matrix P, K plus 1 is F, P, K, and so on. So what you do is you just iterate these two equations. K is the Kalman gain matrix, which or vector, which you're going to be using. R and Q are the covariance matrices of the noise terms, the process noise in Q and the measurement noise in R. And the Kalman filter then is just this kind of, actually just one line really. X hat K plus 1 is Fx hat K given K minus 1 plus K at time. Now that, of course, K at time K means that K is changing with time, but what happens is that if you iterate this in time, if the noise is stationary, what will happen is K converges to a constant value, and it doesn't become K subscript K, it just becomes a constant matrix K, which we can use. So that's important. If, on the other hand, F and some of the other things were varying with time, and we knew how they varied with time, which is unlikely, but let's suppose we did know, then we could have K varying with time and P would vary with time, and the Kalman gain would vary with time as well, and it wouldn't converge. It would just be changing all the time, and that's the more general case. This bit here is like an error signal vector again. That will be. It's actually called the innovations term. That, and you can do the same with. You can get the steady state discrete time Riccati equation, just like you got the continuous time one. So it's where pk plus 1 equals pk, and you just end up with this equation here for p and this equation for k, and they can solve those. But once again, you're going to end up with nasty algebraic equations if you want to solve that. So it's not really that recommended, apart from very simple problems, which are quite nice to do. You can solve them, and then that tells you a little bit of information if you've got closed form solutions, but it's not always possible to do that. So our problem with the MPU6050 is that we have got two lots of sensors. We've got accelerometers and we've got gyros. So I go right back to here, MPU6050. It's called the 6-axis because it's got 3 axes for acceleration and 3 axes for the gyros, which give the angular velocity. So you get angular velocity and you get angular acceleration out of this thing. Just skip forward again. And these are the continuous time equations which link, this is angular velocity, the derivative of angular position. P stands for the pitch, because I'm just going to look at the pitch and the roll separately. I'm not actually going to bother with the roll because the principle is exactly the same. So you need one Kalman filter for the pitch and one for the roll if you're going to do both. I'm just going to do the pitch. Omega dot is acceleration. Omega here is angular velocity, and there's a very simple relationship between that. The minus signs due to gravity acting in the other direction. And we can get the transfer function of this, and it's just a very simple transfer function. So this is our mathematical model, if you like, of it's just the equations of motion. That the pitch angle is the integrated form of these terms, which are noise terms. It gives us a mathematical model of the signals coming out of the thing. And that's the gyro velocity coming out here. And that's integrated white noise as well. If we convert it to discrete time, we've got A is equal to that, B is equal to identity, and C is equal to the identity. It's particularly simple. How we do it, we use that power series thing for a particular TS, it doesn't matter what it is. We see very easily, just for this particular example, because it's got a very simple A matrix, it doesn't work for all problems, that once you start squaring it and cubing it, the value is 0 all the time. So you actually only need these terms here, I plus 1 over 2 factorial ATS. And that gives you the psi, which is equal to that. F is equal to e to the ATS, which is equal to that from the earlier work. And then so you end up with that as the F matrix, a discrete time F matrix. Now, if you work out its eigenvalues, its eigenvalues must be less than 1 for a stable system. Or if it's got integrators in it, they'll have eigenvalues on the unit circle, because that's what integrators have right at z equals 1. You can find G as well, TS psi B, and you get that. If we stick some values in, we get, let's say Q is equal to identity matrix, R is equal to 0.01 times identity matrix. And what I've called here D in the software is equal to G. Then in MATLAB, we can quickly describe a discrete system with these values. We know F, D, and H, and so on. That 0 is because there's no cross covariance term. Actually, that's the reason for that. Actually, is it? Actually, it's here. Sorry, that 0, not the top one. The 0 here is because there's no feed-through term with the state in state space. So most state space descriptions, the general form where x dot equals ax plus bu, y equals cx plus du, and if there's no d term, that's why it's 0. But here, so that gives you the discrete time system, and then you use that in this one line MATLAB command to give us the Kalman gain matrix, which I've done, and it gives you out that. But if there was correlation between the two noise sources, and you happen to know what it was, you could put that in there. And I think in MATLAB they call it the N matrix, but to assume it, usually they're uncorrelated noise. But of course, people have written papers going way back with correlated noise terms. And that's our steady state gains, which we need to use in our filter. So if we implement it, how do we actually implement? Well, you could just implement this top equation here, x hat k plus 1 given k. We know k now. If it's actually that shouldn't be a function of k there. It should be a constant because it's constant values, but never mind. We know s, we'll come to that in a minute, that's the values of the accelerometer and the gyros. So we could implement that. I've suggested, well, what I do is I collect the terms in x hat k given k minus 1. That's the one-step predictor together, and then I get a simpler form x hat k plus 1 given k, and then this bit here is a closed loop matrix of the Kalman filter. Again, I shouldn't have the k there, but it's there anyway. The eigenvalues of this should be within the unit circle again, but it's stable usually, so don't have to worry about that either. So what are the observations, for S, signal plus noise? Well, they come from the accelerometer and the gyro. So if you're doing the pitch, you need the X component and the Y component and the Z component, and it's Rx. That's the acceleration in the X axis, that's acceleration in the Y, and that's acceleration in the Z. It's Rx over the square root of Ry squared plus Rz squared. If you're doing, and that's 57.29 converts it to degrees, and you need the arctan. That's very important. So that gives you the angle already. You don't need a Kalman filter to find that. So that will give you the angle, but it'll be a noisy angle. But it'll be the angle that, that'll be fine, but not perfect. Usually there are ways, I think I explained in the other video, you use it's called a complementary filter if you don't want to use a Kalman filter. And this is just the gyro values on the Y axis. That's the angular velocity. Okay, so you will need that as well. And if you're doing the roll, then it just changes. That Rx becomes Ry, that Ry becomes Rx. Still got Rz there, and that becomes omega x, and then you get a different set of values of data. I'm just going to show you that working, hopefully, if I can. Just put that. So that's the program. I've modified it slightly. It's a few minor errors in the calculations, not for the demo or anything, but when I was working out the values, I noticed that some minor problems. What I've also done here is I've used the MATLAB version of the program, which is to work out the Kalman filter, which is a one-line command. But I've also done it the old-fashioned way by iterating the Riccati equation, those equations I showed you earlier. Update K, update P, and I just did it 500 times. And if you do that, you end up with the same answer, exactly the same answer. And of course, that's because that's what MATLAB is doing anyway. So I'm just going to run this. And when I run it, I get Kalman matrix there, which values I had before. And when I run it the other way, it's here. Actually, I don't put K there, but I can put, there it is. It's the same values when I work it out the second way, just sort of by iterating it around. And I can take the error K minus KD, and it's tiny, it's 10 to the minus 15, indicating that both results are the same. So that's that value. I just want to, I'll come back to that in a minute. I just wanted to show you the program running. And again, I've shown this before, I'll just show it one more time. This is it's written in Arduino code. It's sampled at, it's using a lot of the work by the random nerd tutorials, but they didn't do the Kalman filter bit, and they didn't do the arctan bit in there for some reason. I don't know why. So I had to put them in. But this is my definitions of the the F matrix is there. That's the D or G, depending on what you want to call it. Then I've got my K values I worked out on MATLAB. And these are state estimates. Then this is my closed loop F matrix. Then I set up a timer so that it runs round at 0.01 second or 100 hertz. And I get my angle from the, that's in the Y direction, with the arctan function. The square root part is in here that I showed you earlier. Oops, that's that bit there. And therefore my S, my observations, is the angle and the gyro angle, which are in there. And then the Kalman filter itself is these 4 lines. You need to shuffle the regressors, the pass value. The pass value equals the new value, then the new value is equal to this. And that's that one line. Xk plus 1 is Fc for F closed, X hat K minus 1 plus Ks. And that's the thing running. So I'll just run it quickly and hope you'll just do the serial plotter. And yeah, you should be able to see that. And I've shown it before. So the blue one is the normal accelerometer output. You can't see me moving this, of course, but you can just see the result. The red one is the Kalman filter. You see it's much smoother. If I shake it about a bit, you see the blue one moves quite a lot. The red one doesn't. It's not nearly as sensitive as I'm tilting it back and forward. And you would use this in some kind of control systems that measure the tilt angle, and you could also do for roll. So it could be used as in a quadcopter, for example, or self-balancing machines like a gyro, personal transport type things. So that's that. And the other thing I wanted to show finally was that you can in fact work out do it another way. You can work out what's called the Wiener filter, which we're actually implementing the Wiener filter, but we're doing it in state space form. I normally call that the Kalman filter. So it's a matter of debate whether you call it the Wiener filter or not, but Wiener certainly didn't work things out this way. He did things in other forms. And he didn't do the discrete version. That was done by the Russian engineer Kolmogorov. So here, if we've got the Kalman filter, we can take its transfer function by taking Z transforms. Simply is this K plus 1s, you need a Z term there, times the identity matrix minus FC, so on. And then you invert that, and you end up with this T, I've called it, HZI minus FC to the minus 1K. K is steady state gain. Now that could be nasty to work out manually. It could be quite messy. So fortunately MATLAB does it for us. And you have to do it because it's multivariable. You have to be careful how you do it. But you sort of, it gives you out numerator and denominator polynomials. The numerator one turns out to be like a 2 by 2, and you have to strip off the first row. That's the second row, and so it gives you out the answers column by column, and so you end up with a 2 by 2 matrix of transfer functions, which is that is the Wiener filter. It's not one filter, it's 4 filters as a transfer function matrix. Okay. So I've already converted using MATLAB to these polynomial forms. And this is how you would implement it. That's for pitch, and that's the pitch. I'm not actually plotting the estimate of the velocity, pardon me. But if you wanted it, it's there. I just need to modify the program very slightly. So if you were to implement this in transfer function form rather than state space, you would have theta hat p, actually it should be k, actually there, brackets k, is this filter convolved with that input, plus this filter convolved with the second input, where the first input is the accelerometer output with the arctan, and the second one is the measured values there. And that's about it. So I thought of some loose ends there, trying to explain the finer detail. It's still a little bit complicated if you've not studied state space. So to understand it, you need to study state space first, and then random signals and noise, and it kind of comes together a little bit then. But as you can see, the end result is quite simple, at least. It's not particularly that hard. Thank you very much.